Okay, so thank you everyone. Today I'm going to introduce our paper, Functional Classification with Extremely Weak Supervision. And this work is done by University of Virginia and Arizona State University. And so let's first talk about the problem of functional classification. Here our target is actually to classify and label nodes in novel classes, given that we have abundant label nodes in base classes and also the limited label nodes in novel classes. I can give an example here. So this is a protein-protein interaction network. And so we can see that here the graph is a PPI network, and the nodes represent the proteins and the edges represent physical interactions between nodes. And so we can see that there are some nodes in the base classes and also nodes in the novel classes. Here, the base classes denote the protein properties that are easy to validate, and novel classes denote the protein properties that are harder to validate. So that means we cannot achieve abundant label nodes in the novel classes. And so if we want to classify them, we need to use the functional classification techniques. And the question is how to achieve satisfactory performance. Here, this is strategy. It's very popularly used in the feature learning. So it's that we learn from meta training tasks and generalize our model to meta test tasks. So the process is actually conducted on a series of meta training tasks and meta test tasks. So here we know that if for each meta training task, we have a supporter set, the label nodes as the references. And we also have a query set, which contains the unlabeled nodes for classification. So we know that the nodes in the query set are from the same classes in the supporter set. And so our target is to use the label information in the supporter set to classify nodes in the query set. So after we train our model on a series of meta training tasks, we want to generalize our model to the meta test tasks. The difference is that the nodes in the meta test tasks are sampled from novel classes instead of the base classes. And we know that the meta training tasks will mimic the structures of meta test tasks for generalization. So this is the training, overall training and test process. We want to ask what is the potential drawback here? And so this is a problem of extremely weak supervision. So we first would know that the label nodes in base classes may also be difficult to achieve. So for example, in existing works, we generally assume nodes in base classes are sufficient, which means at least for each base class, we will have hundreds of label nodes. But in real-world scenarios, we know it can also be difficult to achieve nodes in the base classes. That means the number of nodes in each base class may be actually less than 10. So this is the problem of extremely weak supervision because we just have very few label nodes in each base class during training. So this is our problem. And this will cause two challenges. The first challenge is the undergeneralizing caused by insufficient support nodes. So it's like we want to increase the generalization performance of our model by learning from as many as support nodes as possible. But we know if we don't have insufficient support nodes, the generalization performance to novel meta test tasks will be reduced. The second challenge is overfitting caused by insufficient query nodes for model optimization. This is because we will use the query nodes to optimize our model. So if we don't have enough query nodes, we know the model can be easily overfitted to these limited label nodes. These are two challenges. So our framework XFNC proposes to handle these two challenges with two strategies. First, to handle the generalizing problem, we leverage the Poisson label propagation to expand the supporter set. So this is we use this strategy to propagate existing label information to other unlabeled nodes. And to handle our overfitting problem, we want to fine-tune the model while ignoring the irrelevant information via information bottleneck. This is because with the relevant information, the model can be more easily overfitted. So we want to ignore them during training. So this is the principle of the information bottleneck. Here D is the structural and feature information, Y is the label, and Z is the node representations. So here the principle means we want to maximize the label-related mutual information while also minimizing the irrelevant mutual information. So this is the objective of the information bottleneck. So how can we conduct this? So for Python label propagation, we want to propagate the extremely limited labels of the supported nodes to propagate them to the neighboring unlabeled nodes. So in this figure, you can see that in each meta task, we have a supporter set, and we construct a subgraph to incorporate unlabeled nodes. And then we use a Poisson label propagation to propagate the labels from these supporter nodes to unlabeled nodes. So which and then they will become the pseudo-labeled nodes. We also want to select the confidence nodes. So we need to compute the confidence scores and append the nodes with high scores into the supporter set. So the confidence scores is actually very similar to the cross entropy loss. So it's determined by this formula. Here UIJ is the classification probability of the ith node to the J label. So in this way, we can select the pseudo labeled nodes to expand our supporter set for our training. So this is our first strategy. For the second strategy, we use the information bottleneck fine tuning. So notice that our objective is these two terms, and so for the first term, we know it's actually a classification loss. So we will use this formula to classify the nodes in the augmented supporter set as the classification loss. And also we want to optimize the second term. So here we can, with our derivation, we know we can minimize this term. So which is a chiral divergence loss between these two distributions. So for this P distribution and the Q distribution, we use two different GNNs. The first GNN theta, and the second GNN is the GNN phi. And we know that to minimize the chiral divergence between them, we use this loss. We use an additional MLP to predict HI for this HI tilted. So HI and HI tilted are the node representations learned by these two different GNNs. So this is actually a risk construction loss that aims to minimize the chiral divergence between these two terms. And so back in this figure, we can see that because the QZ is not dependent on the D, which is the structural information. So here we use the masked subgraph as input to the GNN phi. So with these two GNNs, we will first conduct fine tuning with these two losses, information bottleneck loss, to fine tune our model GN theta. And finally, we will use these two losses on a query set to finally meta update our model. So this is an information bottleneck fine tuning. With this strategy, we can run our model while maximally ignoring the irrelevant information. If we can also talk about our experiments. So this is a general setting. So for the baselines, we have two types of baselines. For the classic feature learning, we have ProtoNet and the Memo networks. And for the feature node classification baselines, we have GMeta, GPN, and RAIL. For datasets, we have these four datasets, which are widely used in the feature node classification tasks. So we can provide some results here. So we use four datasets, but here, due to space, we only provide the results on one dataset, which is a DBLP. So we can make the following observations. First, our framework XFNC achieves the best feature node classification performance in all datasets with the different numbers of supported samples. So it's like we have two settings, 5-way short, 3-short, and the 10-way 3-short, these two settings. And secondly, the XFNC consistently outperforms the other baselines when a larger value of n is presented. So that means if we change our model setting from 5-way to 10-way, the task becomes more difficult. But our framework still possesses the considerable performance. For a second experiment, we want to conduct an evaluation study. So in this part, we want to validate the importance of two essential modules of XFNC, which are the Poisson label propagation and information bottleneck fine-tuning. So here we have two settings. We have 4 settings, and we own 2 data sets in the casual setting. So n equals 5 and 10, and k equals 3 and 5. From these ablation study results, we can also make observations. First, each module in XFNC actually plays a crucial role in the framework, because we know if we remove one of these modules, the performance will decrease. The second is that without the information bottleneck fine-tuning, the performance decreases rapidly when the number of classes in each task increases. So that means if we change our framework setting to from 5-way to 10-way, and without the information bottleneck fine-tuning, performance will drop greatly. And so now we can draw a conclusion for our work. Our goal is that we want to learn to deal with the feature learning problem under the extremely weak supervision setting. So this setting is not investigated before. The key idea is that we leverage the Poisson label propagation and information bottleneck fine-tuning strategy to handle the 2 challenges under generalizing and overfitting. So if we talk about the advantages of our framework, we know we enhance the generalization performance to metatest tasks with extremely limited label nodes in base classes. For the future work, we may want to leverage unlabeled nodes on the entire graph, because currently we only use the neighboring nodes. So this can be a future work. So this work is supported by these agents. And thank you so much. Do you have any questions?